Modern precision agriculture operates as a closed cyber-physical loop. Field sensors detect environmental conditions and feed that data directly to mechanical actuators. There is no human operator verifying the data before a valve opens or a machine deploys fertilizer. In this four-layer architectural diagram, raw telemetry originates at the sensing layer and travels upward to the application layer. Ground-level inputs automatically trigger crop management routines at the top. These upper layers possess no independent physical awareness. They depend entirely on the hardware sensors. These sensing devices are deployed across hundreds of acres of open farmland. They sit in physically accessible, unmonitored environments where tampering is trivial. Because physical actions are executed automatically and immediately, the integrity of that raw telemetry dictates the health of the crop. A single manipulated false sensor reading can trigger a cascading, irreversible physical response across an entire agricultural zone. The standard approach to securing these IoT networks relies heavily on perimeter defense. Engineers implement AES-128 encryption and message authentication codes to lock down the communication channels. In this LoRaWAN deployment, data flows through an encrypted IP backhaul to the network server. The system authenticates the device's identity, introducing a critical blind spot. It verifies where the message came from, not if the data is true. Once authenticated, the payload is trusted. This structure enables a false data injection attack. If an adversary physically accesses a field sensor and overrides its firmware, they force the device to generate mathematically plausible but factually false environmental data. The compromised device then encrypts this fabricated reading using its legitimate, authorized security keys. The network server receives the packet, verifies the signature, and passes the lie directly into the decision pipeline. A standard hardware fault produces extreme numerical spikes that simple threshold filters easily catch. A stealth false data injection attack is engineered to sit just inside the sensor's acceptable historical limits, mimicking natural environmental drift. If a registered device is manipulated prior to transmission, encryption merely acts as a secure transport mechanism for fraudulent data. Channel security offers zero protection against this authenticated trust loophole. To secure automated pipelines, the architecture must shift from verifying the source to verifying the semantic truth of the data itself. This requires a cross-sensor consensus-based defense framework. Looking at the proposed architecture, we isolate the verification phase at the edge gateway. The process begins in the data collection layer. A min-max hardware check strips out obvious malfunctions, leaving only plausible data streams that might conceal a stealth injection. Evaluating these remaining streams in isolation creates a massive vulnerability. Without an external reference, a well-crafted fake value looks identical to a genuine measurement. The framework breaks this isolation by applying physics-based coherence rules. It forces independent sensor types to corroborate each other's claims. Through spatial co-registration, the system mathematically overlaps telemetry from ground soil sensors with aerial and DVI imagery from drones and proxy data from local weather stations. Consider a scenario where a compromised ground sensor reports extreme drought. If the drone's multispectral imaging shows dense, healthy foliage and the weather station logs heavy recent precipitation, the physical coherence is broken. The system flags the conflict. By enforcing cross-modal validation, an attacker can no longer manipulate a single device. They must simultaneously compromise the ground nodes, the aerial imaging systems, and the meteorological logs to successfully execute a stealth injection. Securing data at the network edge comes with a severe engineering constraint. Agricultural LoRaWAN gateways run on low-power microcontrollers, lacking the memory or processing power to handle heavy AI inference. The framework bypasses this limitation by executing lightweight statistical checks here in the statistical detection layer. It utilizes Welford's online algorithm to update a univariate z-score for each sensor, identifying sudden deviations while requiring almost zero memory overhead. A patient attacker can bypass a z-score by carefully injecting fraudulent values that remain within the sensor's starter deviation. To expose these subtle injections, the framework applies Mahalanobis distance. This evaluates the mathematical relationship between multiple environmental variables simultaneously. As seen in this scatter plot, an injected measurement can sit perfectly within normal limits for soil moisture and air temperature. But evaluated together, the point falls outside the joint covariance matrix. The specific combination is statistically impossible. Traditionally, calculating these full covariance matrices across an entire network exhausts low-power processors, scaling at a steep computational rate. By utilizing a mini-batch covariance estimator, the framework limits the overall computational complexity to a highly efficient O of n squared plus k curve, generating a composite anomaly score without crashing the local hardware. Executing these calculations locally preserves critical bandwidth and ensures that commercially sensitive raw telemetry never has to be transmitted to a centralized cloud server for verification. The architecture achieves robust, multidimensional anomaly detection without exceeding the strict processing boundaries of field-deployed gateways. Once an anomaly is scored, a decentralized group of autonomous sensors must definitively agree to reject a reading. The consensus engine solves this by applying inverse variance weighting, prioritizing historically reliable nodes. It enforces a Byzantine fault-tolerant quorum check, requiring greater than 50% agreement among adjacent sensors to validate a zone. Relying on binary threshold-based alerts in open agricultural environments is dangerous. Sudden benign physical events, like a heavy cloud shadow or localized water pooling, can trigger massive waves of false positives. To maintain stability, the framework utilizes a Bayesian trust update. It treats sensor confidence as a continuous probabilistic score rather than a rigid pass or fail state. When a sensor consistently deviates from the established physical quorum, its trust score decays mathematically over successive reporting cycles. If that trust drops below the initial threshold, the finite state machine automatically shifts the node into a suspect state. Its data is downweighted, and its reporting frequency is doubled for closer monitoring. If the anomaly persists and trust collapses entirely, the state machine shifts the node into full quarantine or blacklists it completely. To prevent a single rogue sensor from halting the entire automated farm, the gateway isolates the compromised node and applies creaking spatial interpolation. It artificially estimates the missing data point based on the verified readings of its healthy neighbors. This adaptive trust mechanism ensures system availability. By mathematically self-healing around a compromised insider, the pipeline maintains operational continuity and never drops an automated decision. We can trace the exact path of a live, stealthy false data injection attack injected into this finalized architecture. Looking at the logic flow, the MQTT broker ingests the payload. Plausible values bypass the hardware check. In the statistical layer, the z-score misses the drift, but Mahalanobis distance detects the cross-modal discrepancy, spiking the anomaly score, forcing quarantine and triggering Kriging imputation. The manipulated telemetry is successfully stripped from the pipeline. The system utilizes multi-layered statistical consensus to intercept cyber-physical fraud directly at the edge, entirely without human intervention. Securing an automated cyber-physical system requires discarding standard perimeter defense assumptions. Cryptographic protections guarantee that data reaches the server exactly as it was sent, but they are completely blind to whether the sensor is telling the truth. When digital data directly actuates physical machinery in the real world, the only viable defense against manipulation is cross-modal physical alignment. Physical coherence must be treated as a mandatory cryptographic primitive. It is just as critical to the integrity of precision agriculture as the encryption algorithms securing the airwaves. In a fully automated infrastructure, engineers must design under the assumption that the sensor is inherently hostile. True operational security no longer exists in a verified identity, but exclusively within mathematical consensus.